Hello everyone, this is Brenna, your friendly 121LA, here this week with a problem about pressure and flow through tubes and things like that. So this problem is pretty complicated, but I'm going to go through it step by step and hopefully we get there. So when you breathe deeply, you pull in 4 liters of air in about 3 seconds. This requires a pressure difference of about 4 kilopascals between the air in your lungs and the outside air. What additional pressure difference would be required to pull 20 degrees Celsius air through a skinny straw that is 22 centimeters long and 0.38 centimeters in diameter? We'll consider 2 factors. What additional pressure is necessary to get the air up to speed? What is the pressure difference across the straw to maintain this speed? Okay, so let's first draw a picture because I have a hard time visualizing these things. My picture is going to be very simple. I'm going to have a picture with no straw, and I'm going to have a picture with the straw. Okay, and we'll say this side is the lungs. Nope, I did that backwards. I don't want to do that side the lungs. That doesn't make any sense. This side is outside. This side is the lungs. Same with this side, except now we have a straw. So we have the outside. And then we have the lungs. And we know in our first case that the pressure differential across from the outside to the lungs is 4 kilopascals. We also know that 4 liters of air goes in every 3 seconds. So we have that rate. Well, I know the pressure outside, it's about 85 kPa. So if I have a pressure difference of 4 kilopascals from the lungs to the outside, then my pressure inside the lungs is going to be 81 kilopascals. Well, in the second scenario, the outside pressure does not change, right? We're trying to find the new pressure differential with the straw when we know that it is 20 degrees Celsius outside. And what else do we know? We know that the, I forget the viscosity of the fluid is, whatever this Greek letter is called, 1.8 times 10 to the negative 5th Pascal seconds. And what else do we know? We know that the diameter of the tube is 0.38 centimeters. And the radius, the length of the tube is 22 centimeters. We want to find what the pressure differential is. Because we know that the pressure differential in this case is greater than the first case, that means that the pressure inside the lungs must be greater than 85 kilopascals. That's the only way we can get a greater delta P. Okay, so first we're asked, what additional pressure is necessary to get the air up to the greater speed? Okay, well, first we need to look at speed then. So we're going to solve for speed. Solve for speed. Well, if we're talking about speed, we're probably talking about flow. And we know that flow is equal to Q, which is also equal to the volume in meters cubed divided by the time, and that is equal to the average velocity times the cross-sectional area of the tube, right? So we need to find basically the speed of the air through the tube. So let's go ahead and do that. We know that the volume is 4 liters. Turns out that 4 liters is 0.004 meters cubed. So we can say that 0.004 meters cubed over 3 seconds is equal to the average speed times the cross-sectional area of the tube. And since the tube is circular, the cross-sectional area is just going to be pi r squared. We know pi, of course. The r is going to be half of the diameter, so 1/2 0.38 centimeters, but it has to be in meters. So we're taking 1/2 of 0.0038 meters. Let me scooch this over a little bit. That whole shenanigan is squared. And then we can solve for our average velocity. So if we go ahead and do that, you get a number that is 117.56 meters per second. So that's our speed, but we want to find delta P. We need delta P. Well, in order to find delta P, we need to find the pressure in the lungs, right? We can find P2 by using Bernoulli's equation, and since we're not really focusing on a vertical component, we don't need to include the vertical component of Bernoulli's equation. So if we go ahead and write down Bernoulli's equation without, well, let me erase these two dots here. Bernoulli's equation without vertical piece. That equation is going to look like P1 plus 1/2 the density of the fluid, initial velocity squared, is equal to the final pressure, or P2, plus 1/2 the density of the fluid times the final speed squared. Okay, well, I know that the speed in the first case, before the air even goes into the tube, is 0. So this term cancels out. P1 is the pressure outside, which is 85 kilopascals, but we have to convert that to pascals. So we need to do that. P2 is going to be the pressure in the lungs. We know that, I'll scoot this over, oops, sorry. Scoot this over a little bit. We know that the density of air is just 1. And our final speed we just found is 117.56 meters per second. So if we rearrange this to solve for P2, we say that P2 is equal to P1 minus 1/2 the density times the final velocity squared. Let me go ahead and shrink this up a little bit, scoot it down. We need plenty of room for this problem. And if we go ahead and do that calculation, we get that the pressure in the lungs is about 78.1 kilopascals. Well, if we were to assess right here, this is above 85 kilopascals, which we predicted. So yeah, it checks out. Now, we need to find the pressure differential across the outside to the lungs, right? So delta P is just going to be P2 minus P1. P2 is 78 kilopascals. And P1 is 85 kilopascals. We get a delta P of 6.9, yes, kilopascals from the outside into the lungs. But that's not all we're asked. We're also asked, what is the pressure difference across the straw to maintain this speed? All right, so I'm going to go ahead and move over here. So if we're looking for pressure difference, well, we'll do it like this. Delta P across straw. We're looking at flow across a tube. And we have an equation to tell us the pressure difference across a tube. And this is something that you go over in class, but it's a recombination of Poiseuille's law. So delta P is equal to 8 times whatever that Greek letter is, times the length of the tube, times the average velocity, over the radius of the tube squared. Well, we have all of this information, right? We know that, delta P is equal to 8 times whatever that letter is, which we found out that it was 1.8 times 10 to the negative 5th Pascal seconds. That's in the original problem. Times the length of the tube, which is 22 centimeters, but we need it in meters, so 0.22 meters, times the average velocity, which is 117.56 meters per second. All of that over the radius squared, which is going to be 1/2 the diameter in meters, so 0.0038 meters, that whole thing squared. And if we calculate that out, we get about, what is it? It's like 1,000 pascals, which is going to be equal to 1 kilopascal. So the pressure difference across the straw is going to be 1 kilopascal. And so the total pressure difference that we looked at up here, what additional pressure difference would be required to pull 20 degrees Celsius air through a skinny straw that is 20 centimeters long and 0.38 centimeters in diameter, we need to add this number to this one, because that's going to be the total pressure difference across that system. So total delta P is going to be equal to 7.9 kilopascals. We're asked to find the additional pressure. So if we subtract 4 kilopascals from our original system without the straw, we get 3.9 kilopascals of additional pressure difference. And this is a pretty good amount. I mean, that's 3,900 pascals of pressure, right? You could convert that to PSI if you wanted to, but I think that this makes sense because it does require a bit of extra pressure. We can see that the pressure inside your lungs has to be significantly greater with the straw than without the straw. So with somebody, like it says, a person doing the Strawfie challenge to bring aware to the situation of people with cystic fibrosis or other breathing ailments, it's hard for them to get air into their lungs. So yeah, this kind of makes sense because it is going to be harder to get air into your lungs when you have that pressure differential that we talked about. So I would say this makes sense. And I think that is all. I will catch you in the next one.